say we start off with two objects here. We'll call first object object number 1, and we'll make it have a velocity of 10 meters per second with a mass of 20 kilograms. So let's say it's moving to the right at 10 meters per second. It strikes object number 2, which is initially at rest, just sitting there at 0 meters per second. We're going to give it a mass of 25 kilograms. Let's say that after this collision takes place, these two objects stick together. They go off as one object. So object number 1 has a momentum to the right, object number 2 has 0 momentum. After they collide, they both combined have a momentum that's to the right. How do we analyze this problem? We know what to do with this. We've done a lot of problems like this so far. We know that PI is equal to PF. How many objects do we have before this collision takes place? 2. So let's say we got 2 objects, we got 2 terms. M1 V1I plus M2 V2I. How many objects do we have after this collision takes place? 1. So let's say 1 object, 1 term, M times VF. So far so good? So bring in a bell from before the break. Let's plug in some numbers here. M1 has a value of 20 kilograms. V1I has a value of 10 meters per second. M2 is 25 kilograms. What's V2I? 0. So I'm going to just X this out. I'm going to add to that 0, but in the end I could leave that entire term off if I wanted to because it has no value. If I add 0 or if I leave it off, it has the exact same effect. What's M over here on the right-hand side? These two objects are sticking together. What's M on the right-hand side? 45 kilograms. VF, we don't know what it is. We're going to find that. Do the math on that, and VF works out to be 4.4444. Now, if this was a final answer, I would round it to 2 digits, 4.4, but I guess the problem that you see up on the board thus far, it is a final answer, but I'm not really through with this yet. Okay, we're going to take this and we're going to use it a little bit later on. So we're going to leave the unrounded number so that we can use it later on as the unrounded number. Is that okay? Okay, if that's a question on a test, we have to get that right. Okay, we can't afford to get that right. We're not going to get 80 if we don't get that question right. Okay, we're probably not going to get 70 if we don't get that question right. Let's take a look at another one. This time we have object number 1 that's at rest. It has a mass still of 20 kilograms, just like it did in the last question. Object number 2 is this time traveling to the south. It has a mass still of 25 kilograms. This time it has a velocity of 15 meters per second to the south. After these two objects collide, they're going to stick together and go off as one object. So object number 2 has a certain momentum to the south before the collision. Object number 1 has nothing. Combined after the collision, they're going to have a momentum to the south. That's that green line there, that green momentum. We're going to analyze this more or less the same way as we analyzed the last question, using conservation of momentum. PI is equal to PF. There's 2 objects before the collision, M1 V1I plus M2 V2I. And there's 1 object afterwards, MVF. M1 is 20 kilograms. What's V1? What's V1I? What is it? Good. It's 0. Why is it 0, Jared? The first object isn't moving. It tells me, right in the question, that the initial velocity is 0 meters per second. So let's cross that off. If I want to put in a 0 there, I can. Or if I want to just leave that off, I can do that as well. M2 is 25 kilograms. Tell me what the value of V2I is. Christine, what's V2I? Almost. Not 15, but what's she missing there? Negative 15. We're going to make it negative 15 because it's going to the south. Now, the exception to that would be if you defined south as positive, which you could do, but I'll never do, especially in a 2-dimensional collision. It's not wrong, but there's a good chance it'll lead you to making a mistake somewhere down the road. That combined mass is, once again, 45 kilograms. We're going to multiply that by VF. Solve for VF here. It is the y component of VF. Works out to be negative 8.33. Is that okay? So we've just done two problems, both of which we need to be able to get. Both of which I think we can all get. Yeah, I think unless we make a silly mistake on it, I think we're all going to get the correct answer for those. I hope so. Now let's take a look at one more problem, the third problem here. Let's say this time object number 1 is going to the right. It has a velocity of 10 meters per second. It has a mass of 20 kilograms. That's exactly the same as object number 1 in the first problem, right? Now let's say object number 2 that has a mass of 25 kilograms is going downward at a velocity of 15 meters per second. That's exactly the same as object number 2 in the second problem, agreed? Let's say they collide right here. Where are they going to go after they collide? If they stick together, that is, where are they going to go? Good. Diagonally down and to the right. We know that because momentum has to be conserved. And if there was eastward momentum before the collision, there has to be eastward momentum after the collision. If there was southward momentum before the collision, there has to be southward momentum after the collision. So we know that it's going to go down to the right somewhere. 45 degrees, I don't know what angle, but I know it's going to go down and to the right somewhere. Now what we're going to do with this is analyze it as two separate problems, an x problem and a y problem. What's neat about this is that the x problem is exactly the same as the first problem that we just did. In fact, it's not only close to being the same, it's exactly the same. So much so that I can actually copy and paste the work that I did. I don't like that. I can copy over the work that I did in question number 1. Why is it okay to do the exact same thing for the x component of this problem that I did for the first problem that we did today? Dylan?
Because object 1 is the same givens as it does in the first problem.
Okay, but object 2 doesn't, right? Object 1 does have the same givens as it does in the first problem, but object number 2 doesn't. Okay, keep going.
However, the invariant both objects are still stick together.
Right?
So,
But how do we, you're right, they do stick together, but how do we justify the fact that in question number 3, object number 2 is moving, in question number 1, it isn't moving, but yet we're doing the exact same thing? Good. When we're analyzing the x, let's take a look at just x for a second, okay? If we take a look at just x, we can effectively cover up everything that's y. Let's cover up object number 2 here. If we cover up object number 2, it has no momentum. There's nothing there. So it becomes the exact same problem as we had with problem number 1. Let's try the same thing now for the y component, except for the y component, we're not going to copy over question number 1, we're going to copy over question number 2. When we're dealing with the y component, we're ignoring everything x. So basically, it allows us to treat it exactly the same as we did for the question that was just a y component. You understand that? If we've got a two-dimensional problem, or what we call a non-collinear problem, a two-dimensional problem, then we can treat it as two separate, easy problems. An x problem and a y problem. The x problem we've done a million times before. The y problem we've done a million times before. We just haven't done them together. Now we're doing them together. In a sense, we're still doing them separately, but we're doing them as part of one question. We're not quite done yet, though. We haven't found the final velocity yet. We've found the x component of the final velocity and the y component of the final velocity. I need the overall final velocity. Can anybody suggest how we're going to do that? Let's try the Pythagorean Theorem. Let's draw a vector diagram first. We've got 4.44 to the right. We've got 8.33 that's downward. The resultant velocity will be from start to finish. The angle is always going to be drawn in here at the beginning of the diagram. When we solve for v here, using the Pythagorean Theorem, it's going to work out to be 9.4 meters per second. And square root of 4.4 squared plus 8.3 squared equals 9.4. Let's find the angle by using the inverse tan function. This is back in physics 20 now, right? We did this a million times in physics 20. The inverse tan of opposite over adjacent. Opposite is 8.33 over 4.44. Theta works out to be 62 degrees. What would the angle be there? 62 degrees what of what? It's south and it's east, right? Is it east of south or south of east? Done. South of east. Right, we're measuring the angle from the east, south from east. It's not measured from the south, it's measured from the east. So south of east. Anybody ever have trouble knowing where to put the angle? Here, here, here? Always put the angle at the start of the vector diagram. So where you see tail to tail, not where you see head to head. Is that question really a lot harder than the questions we did last week? No, I don't think it's harder at all. I really don't. I think it's more work. In fact, it's 3 times more work. But it's not harder. Oh, good question. Good question, yes. The question is, if you didn't hear that, is if we do the triangle differently, say 8.33 this way, that's correct, right? 4.44 over this way? Yeah, that's correct as well, because, and the rules of drawing vector diagrams don't say anything about which order you have to do it in. I can walk 10 meters to the north and then 5 meters to the east, or 5 east and 10 north and end up in the same place, right? So it doesn't matter what order I draw them in, but when we do that, unfortunately, we're going to get a speed that's the same. But the angle is going to work out to be different. That angle is going to work out to be 38 degrees. But that angle is not measured from the east this time, it's measured from the south. So it would be not south of east, it would be south east of south. Now, which one's right? They're both right. Be careful, on a multiple choice test, it's going to specify whether they want east of south or south of east. So know what you're looking for, right? When you see the answers, look at it and say, okay, I got east of south, I got to turn it into south of east, or vice versa. If it's a written response test, which you'll have on this topic here in a few weeks, 2 or 3 weeks, it doesn't matter which way you do it in. Yeah, yeah, it'd be 28, yeah, thank you. Sorry, it'd be 28. Didn't drink enough water today. 28 degrees east of south. Is that good? Christine, was that why your hand was up, to point at the math error? Then you'd be wrong. If you do it this way and put the angle down here, you would get 62 degrees. Okay, if you put it here and get 28 degrees, well, that's wrong as well. I mean, unless you expressed it as 20 degrees east of south, but it's drawn improperly. But if it got you the right answer, it would get marked right? But you don't want to get the right answer by drawing it wrong, because at some point you're going to mess up on that, right? Does that make sense? You guys feel comfortable with this? What I don't want you to do when you see one of these two-dimensional problems, like you do the third problem over here, is, first of all, I don't want you to just say pi equals pf. You can't do that. If there's 2 dimensions, then you've got to do pi equals pf twice. In fact, you can see how if this was in space, and there was an object coming this way, and an object coming this way, and an object coming this way, you'd have to break it up into x, y, and z. We won't have to do that. But you can see how you would break it up into x, y, and z components. Hey, we'll limit it in physics 30 to 2 dimensions, x and y. It doesn't make it harder. X, y, and z even doesn't make it harder. It just makes it more work. That's all. So don't leave it as just pi equals pf. Break it up into the 2 components. But don't panic about that either. You look at it and say, it's really just those first 2 problems combined. So solve the first two problems and then combine them using some trigonometry and the Pythagorean theorem. If we can get those first two problems, we can get that third problem as well. All right, let's take a look at a couple practice problems. Those practice problems are on page 492. Let's see what we can do with them over the next few minutes. A couple of little notation things that I want to point out to you before you start. This 90 degrees means upwards, and 180 degrees means to the left. The answer there says 131 degrees. We're going to express that as 41 degrees this way, or you could express it as 49 degrees, I should say, this way. So don't worry about getting 131. If you get 49 degrees north of west, or 41 degrees west of north, you're correct. Don't worry about the 131 at all. That's a notation that they use in this textbook, but that we don't see on exams. So we're not going to lose any sleep over that notation. Just the concept is the important thing here. Okay, let's give it a try here, and we'll see what you can do over the next 10 minutes or so. If we have no problems with those, let's take a look at one more example for the day here. 9.14 on page 495, Jared. That's page 495. Don't get mixed up with that, Jared. This one says a 0.60 kilogram fireworks bundle is at rest just before it explodes into 3 fragments. A 0.2 kilogram fragment flies west, and then we've got a 0.18 kilogram fragment flying to the south. Notice I've circled both of those, the west and south, because we've got 2 different directions here. In fact, this is even bigger than we had before with 2 different directions, a north and a south, because this time we've got to break it up into x and y components, not just worry about positives and negatives. We want to find the velocity of the third piece just after the explosion. Let's draw the picture here. We'll make this my explosion point, x. X marks the spot. We have a 0.20 kilogram fragment. We'll call it piece number 1. It has a mass of 0.20 kilograms and a velocity of 14.6 meters per second after the explosion has taken place. Object number 2, or object B, whatever you want to call it, is moving to the south after the explosion takes place. Its mass is 0.18 kilograms, and its velocity is 19.2 meters per second. There's a third piece. Where does that third piece go? Roughly, at least, where does that third piece go? Justina? Good, up and to the right. We know it's going to go up and to the right because the initial momentum was 0, the final momentum has to be 0. If we have a momentum to the left after the explosion, then we must have a momentum to the right to balance it. If we have a momentum downward after the explosion, then we must have a momentum upward to balance it. Let's break it up into x's and y's. Let's say pi is equal to pf. How many objects do we have before this explosion takes place? 1, good. What's its momentum? 0, it's at rest. So if I want to, I can just put in a 0 here without putting any variables or any terms. Just put a 0 there, representing the entire term, the entire momentum before the explosion has taken place. How many objects do we have after it's taken place? Jared, what do we get afterwards? 3. M1 V1F plus M2 V2F plus M3 V3F. 3 objects, 3 terms. M1 has a mass of 0.20 kilograms. What's V1F? Remember, we're analyzing the x component here now, so we're covering up anything y. Covering up the object number 2 here. What's V1F? Have we covered that up? No. So what's V1F? 14.6, almost. We're going to make it negative 14.6 because it's to the left. Good. M2. What's the mass of object 2? 0.18, but yeah, you get a better answer. It doesn't matter. It doesn't matter because V2F is 0. Why is V2F 0? Good, it's going on the y-axis. We cover it up, right, because it's going on the y-axis. How much of it is x? None. So we cross off that entire term. M3 is, we don't know its mass, do we? We don't know M or V, do we? Can we find M pretty easy? Christine, how are we going to get M? Any idea? No? Go on.
Take the original mass before the explosion and then just subtract the other two masses.
Right. We start off with 0.6. We lose 0.2 and 0.18 from object 1 and object 2, so we're left with 0.22 kilograms left for object number 3. Does that make sense, everyone? It's a little thing, but it's one of those things you got to think outside the box a little bit. A little bit tough there. Solve for V3F. What does it work out to be? 13.272727 meters per second. Let's go with the unrounded number there because it's not a final answer, right? We want unrounded numbers until we get to the final answer. Let's go through the y components now. Let's say pi is equal to pf. Once again, we'll say 0 initial momentum because it's at rest. Hey, if this fireworks bundle was moving before the explosion took place, well, we wouldn't say it was 0 momentum, would we? We'd say it's MVI. It wouldn't make it that much harder, just a little bit more math to it. 3 objects afterwards, 3 terms, M1 V1F plus M2 V2F plus M3 V3F. M1 is 0.2 kilograms. What's V1F? Jordan, what's V1F? What? Yes. Yes, good. Exactly. We're covering that up, right? We're covering up everything that's not y. So if that means we're covering up object number 1, it has no velocity. At least in the y direction, it has no velocity. Therefore, it has no momentum. So cross it off. M2 is 0.18 kilograms. V2F is, we know this one, right? What's V2F? Good, almost. Negative 19.2, yeah. And M3 is, of course, 0.22 kilograms times V3F. We end up solving for the V3F. What does that work out to be? Positive something? $15.70970999. Oh, okay, 0909. Okay, thank you. This is exactly the same as what we just did, right, with the collisions, except that our initial momentum is 0 this time instead of something. We got one object splitting apart into 2 or more instead of 2 or more coming together to form 1. Let's do the last little bit here now. Let's redraw it as a vector diagram. We've got 13.272727. We've got 15.7090909. Remember that these vector diagrams are always drawn head to tail, okay? Front to back. Never front to front, never back to back. The resultant vector is drawn from start to finish. And the angle is always drawn down here at the beginning. This is the easy part now, right? We're going to say V is 15.7090909 squared plus 13.272727 squared. Let's square root that. What do we get for V? We get 20.6 meters per second. We've got to find the angle. The angle is always drawn from the start of the vector diagram, not the end. The angle is going to be the inverse tan function of opposite over adjacent, so 15.70909 over 13.27. What do you end up getting for that? Somewhere around, I'm going to guess 47, 48, 49.6, okay. 49.8 degrees, okay, thank you. 49.8 degrees, how would we express that? 49.8 degrees what of what, Michael? That would be north of east, right? Because the angle is measured from the east, right? From the x-axis. If it's touching the x-axis, it's from east. And of course, it goes north from there, so it's north of east, north from east. If somebody else had drawn that the other way around, drawn the y-axis first and then the x, they would have got an angle of 40.2 degrees. 40.2 degrees, not north of east, but 40.2 degrees east of north, and both are correct. Just recognize how to get one from the other, just in case on an exam they only give you one of those options. Is that good? All right, what I'd like you to try now is question number 1 and 2 that appear on page 495. I'm going to put a little star by question number 2 because it's a bit of a challenge question. It actually takes us a little bit of a step beyond the example that we just did. I want to see what you can do with it, but if you have trouble with it, I'll help you with it. Okay, and we'll certainly go over it if we need to. Question number 1 is just like what we've just done. Question number 2, as I say, is a bit of a step up from it. See what you can do.